categorical by categorical. See how that goes. For that, we, in the end, need to be able to do two kinds of tests. One is called a Chi² test, and the other is called a Fisher's exact test. And basically, these are the only two that we need. In fact, in Stata, it's really easy. So in the end, what you should be able to do is only this. This is what it looks like. First, you have two variables, x and y, and x and y are each categorical. Doesn't matter how many categories they have. What you want to do is make sure that you create a crosstab and look at the table. You do that through tab xy. Then you check all the cell counts. One cell will contain the frequency of the number of cases that you have. So if you have, let's say, an x variable with 5 categories and a y variable also with 5 categories, then in cell number 1, 1, you'll see how the number there, how many cases are in that cell. You check if these are all at least 5. This is the standard rule of thumb. In fact, there are a couple more rules of thumb in the book, but that's usually what we go by. If that works out, so we have indeed at least 5, then we do tab xy, chi². And if we don't have that, then we do something else that's called Fisher's exact, and that you do through tab xy, exact. That will give you output. The output, once again, has a number in there, an actual test of the thing that we're testing here. And what we're testing here is that, well, this is the H0, more on this in a minute. All columns are distributed in an equal way, namely according to the marginal. That's the thing that we're testing. Sounds complicated, but actually it's not so bad. Then you get a value that is either above or below 0.05, and depending on what you get there, you either reject or you support that H0. So that's basically the thing that you need to do. It takes a longer while to explain why this is what you need to do and what is exactly happening behind the scenes, but this is basically it. Okay, I need a bit of a run-up there. First, a little bit of statistics. This I had on the slide deck before. This is the normal distribution, where we actually have a formula there that goes with the normal distribution, and if you look closely, you even see here that this is not exactly the graph here that belongs to that one, because here you see a mu in there, that's actually the midpoint of that distribution, which is 0 over there, and the sigma squared, and that is how wide this distance is, here from 0 to 1, but in principle that could be any number. Okay, so that we went through already. We know the formula, so if you want to calculate on this stuff, that's, well, may not be easy, but at least it's possible. You have an exact formula and you can try to work with it. A couple of rules that are handy to know. First, if you have this, a variable x, that is this tilde over there is meant to suggest is distributed as a normal distribution with a mean mu and a variance sigma squared. So the middle is at mu, and sigma squared says something about how wide it is. Then if I create a new variable where I subtract that mu first, and then divide by that sigma, then I get something that is normal with a mean of 0 and a standard deviation of 1. So if need be, if I have something that has a normal distribution, doesn't matter where exactly it is or how wide it is, as long as the shape is normal and follows that formula, I can create a new variable from that is actually 0, 1 distributed. That's one calculation rule. Anything that has a normal distribution can be made standard normal if you want to. And the other one is if I have two variables, an x1 that is mu1 and sigma1 squared distributed, and an x2, same thing, and I create a new one as the sum of the one that I had, then, well, the first part is relatively easy to see. The new midpoint of that normal distribution is at mu1 plus mu2. You simply add the two humps together, and the variance, so how wide the thing is simply the sum of these square numbers that we had in the beginning. So if you sum up two normally distributed variables, you get something else that is, again, normal. Perhaps not so easy to see if you think about, okay, if I have something that looks like this, and I add it to something that looks like that is perhaps way smaller, well, if you add that, then again you get something that has a shape like this. Not that intuitive, I guess. If you want to go through the proofs, these are not very easy. On the Wikipedia page that I referenced to here, you see a couple of examples of proofs, or quite a few, and the three that are there, all are not so nice. If you want to do this, you need some serious calculus, for instance, or some other stuff that you need to really know well. But in any case, the formulas themselves are relatively easy. So we can calculate not only with a single normal distribution, but also add them up and create different ones. Okay. Now, a new statistic that we create based on that normal distribution. In fact, when I gave a slide at some point with a long list of theoretical distributions, this one was also in there. It's called a chi² distribution. What is that? A chi² distribution of degree k. That's the sum of k² independent standard normal variables. Okay, let's do that slowly. So, if x is a draw from a standard normal distribution, that n01 that we saw on the previous slide, then I can also create, instead of x itself, x², that also has a distribution. I have the formula for standard normal, so I can square that and get something that has a different distribution, and that thing is then called chi² with degree 1, where the 1 is representing the fact that we have only one variable in there. Can do the same thing. Now for two variables, if a is from a normal distribution, I draw from that normal distribution, I square that number. B is also from a normal distribution, I draw from that normal distribution, I square it, and now I add them up. Now it's again a chi² distribution, but now of degree 2. So that degree says something about how many different squared normal distributions I add up. Well, first thing to see here is, well, obviously that you have here only positive numbers. You can't have anything else. And you also see that as the k goes up, so the more of these different numbers you add up, the more, let's say, the bulk of the data points is moving towards the right. So it starts with these two, and then where you have a hump sort of on the left, more to the right, more to the right, more to the right. And the more you add them up, the more that thing is moving towards the right. Okay, and have that separately here as well. Okay, so in principle you could simply think, yeah, nice to know, I will need that in a minute. But in principle it's simply using the formula that I have from the standard normal distribution and then doing something with it. And at this point it's not obvious at all why we would actually need this, but in a minute I hope it will be, or at least more so. Okay, that is the statistics background that we need. Now on to two categorical variables from our own data. Here I'm using the actual data that I got from, I think, a year ago. So these are not the cell counts or the frequencies that we have in our data. But we could do it in the same way in our data. Here we have male-female on top. So 63% in this case is male and the rest is female. And I asked, how do you go to TUE by on foot, by bike, by bus, by train, or by private transport. And you get a certain distribution. So indeed, these are two variables here, x and y. Both of them are categorical. And now I'm on my way to try to come up with a chi² test. So first let's see what in the end we want to be able to accomplish. Here you see that command that I started about in the beginning. Tab, female is one variable. Variable to TUE, that's the other one. And, well, you can forget the row for a minute, then you get the chi² behind it. And indeed, in the end, you get a number there, in this case 0.122, that says something about whether or not H0 has been supported or has been rejected. Yeah, let's see, one thing that you figure out if you improve these kind of things over the years is that if you do it like this, now you see how you travel to TUE most of the time, and then you don't see anything anymore, and the only thing you see is 1, 2, 3, 4, 5, and you have to cross-reference with the survey PDF to see what 1, 2, 3, 4, and 5 are. So usually it's a wise idea to put in the label something like this, where the numbers actually are already showing exactly what it is. But this is what we're trying to figure out. What is that? And I have the same crosstab actually here. Let's see, I have to peek there, yeah. This is the same table as on the previous slide. The only thing that I left out here are the cell counts. And the thing that I leave standing over there are the numbers on the edges, and another word for that are the marginals. Even in Dutch that's a word, marginale. So in this case we have 72 males and 36 females, and well, we're trying to figure out if there is a difference across these different columns from left to right compared to this difference over there. So if these two, being male-female, and which mode of transportation you choose, would not be related, and if we know that there are 70% males and 30% females, well, then we would expect, if none of that makes a difference, that we would get that 70-30% here as well. And 70-30% there as well, and there, and there, and there. That would mean it doesn't matter if we somehow partial out the different ways of transportation to TUE, you get that division 70-30 all the time. Now what would that mean? That would mean that if I have this table, you have here the same table again, now in red, I have the numbers there that I would, oh, it's not 70-30, it's actually 2/3 versus 1/3. In red you see the numbers that I would expect if this would be exactly right. So I get 2/3 versus 1/3 in each and every one of these columns. So that's a 2 here and a 1 there, a 16 here and an 8 there, a 2.7 here and a 1.3 there. This of course can never happen because there has to be an integer in there. You can have 3 cases there or 2, but not 2.7. 49.3 versus 24.7, and again 2 versus 1. So this is what I would expect if they are totally independent and everything works out just perfectly. Okay, so now we see a little bit more intuitively what that H0 is. H0 is, well, we expect no differences in the sense that we expect the red numbers over there. Across all the columns, that distribution should be the same. Okay, now we have in gray the actual numbers that we have. So the next thing we need to try to figure out is we should compare the gray numbers that we have here with the red ones that we expect if there are no relations between the two. Well, there are many ways in which to do it, but the smart way to do it, and in the end we'll find out why it's so smart, is doing something like this. We compare the cell counts one by one in the following way. All the same, all the same, the two top tables, you see 3 minus 2 squared over 2. That is that difference here between the 3, the gray 3 over there, and the 2 over there. That difference I square to make sure that I do not add up a -1 and a +1 to conclude erroneously that there is no difference anymore. So I square this difference, and I take into account that I had 2 here as a measure for comparison. Would make a large difference if I had 100 here and then I'm missing only 1 versus I had 2 here and I'm missing only 1. So I take that into account. I do the same thing for each and every one of these cell counts. 45 there, 49.3. I subtract the 2, I square it, and I divide by the 49.3 as a reference point, so to speak. I do that all the way through to 3 minus 2.7, and I would put the other way here, but I wouldn't have fit on the line. The 1 minus the 2 squared divided by 1, and then in the end we add that all up and we get a number, 7.27. Now, forget for a minute exactly how this is done, but in any case you can see here, the bigger the differences are, the bigger that number on the right is going to be. So, in a way we are in the same situation where we were with the coin flips. There we were also trying to do something of the same kind. We had 1,000 coin flips, and we know, yeah, we're expecting 500, and we're trying to figure out where the number is, 525, 600, 700, where it starts to be weird. And here, this is actually the same thing. So that 7.27, it would be nice if you could say something about, is that a high number? Should we expect this, or shouldn't we? And that's exactly what we're going to do here. And what is going to help us here is that this thing over there, that sum of square differences, about that we know that this is approximately chi² distributed with 4 degrees of freedom. Okay, that is not something I want to go into in detail exactly how. You can see it coming sort of, that these squares are squares of standard normals in the long run through the central limit theorem. So, you know, forget why exactly this is the case, but again, this is a known distribution, and the only thing that is not helping us very much is that it is approximately distributed as something like this. So we have something to go on, but it need not be good enough. Okay, yeah, and just to remind you of that coin flip example, this is exactly the same thing. coin flips, we have a distribution that we know, and we're trying to find the edge. Where does it start to be weird? Same thing here for the crosstabs. Okay, so let's see, in Stata, what does that do? We have, and here I have the original table that I had a couple of slides ago. Here I have that same table. Now I added a little bit, something over there. It's called X for expectation. So the numbers that I put in red, you can actually get them from Stata as well if you want. There's no need to necessarily, because Stata will do the math for you. But in any case, here you do see the expected numbers over there: 2.0, 1.0, 49.3, 24.7, and so on. You also see that 7.27 in the end, that's the sum of square differences. So Stata is doing all this behind the scenes, and you get, using that we know the chi-squared distribution with 4 degrees of freedom, you get a probability in the end. And what is that again? That is the probability that if H0 would be true, that we get data that we have, or data that is even further away from H0. And that here is 0.12 above 5%. So this means H0 is supported, or stated differently, H0 is not rejected. Okay, so apparently here, in this case, there is no reason to really believe that there is dependence between being boy or girl versus what kind of mode of transportation that you take to TUE. Let's see, we could do something else here as well. You could, for instance, look at these tables and see that the first and the last column, and the third in fact, all three, don't have so many cases in there. So there are a couple of people actually who come on foot, and also a couple who come by bus, and a couple by car or motorcycle, but that's just only a handful. So if you really want to make an actual comparison, perhaps we should restrict the comparison to only these two columns, that one over there and that one over there. And that's easily possible through the same syntax by adding an if command behind the tag. All this is the same thing, tag female travel to TUE row chi-squared, and then you add if travel to TUE equal to 2, where we once again need the double equal sign for in value equal to. This is an or, you have over there, and then travel to TUE double equal 4. And then you only get the two columns, let's see, bike versus train. Now you see that the three columns that we had before have disappeared from the actual table. And in fact, now, running exactly the same test, you do get a value over there that is, well, it's only slightly, but it is below 0.05. So here we do see differences between boys and girls with respect to what kind of mode of transportation they use. In this case, we find H0 is rejected, contrary to what we had before. Yeah, and in blue, just so you wondered, you might think that that whole exercise that I did, where I went through it column by column, does it make a difference if I interchange the columns and the rows? And the answer is no. So you could, if you would have a 10 by 10 table, and you square these differences either row by row or column by column, none of that makes any difference. So luckily, if you type tab XY or tab YX, that won't change a thing.